Hello, my name is Julissa Rodriguez and I am a second year student studying in the field of basic sciences. Today, I have the opportunity to explore and present a fascinating topic in the world of physics, which is the fluid dynamics. This field investigates how fluids, or liquid and gases, move and behave under the various forces. Among the key concepts in fluids dynamics are the equation of continuity, which helps explain the conservation of mass in fluid flow, and Bernoulli's principles, which reveals the relationship between pressure, velocity, and height in a flowing fluid. Additionally, we'll look at surface tension, the force that allows liquid to form drops and interact with surfaces, and viscosity, which determines a fluid's internal resistance to flow. So now, let's discuss first the Module 2, Lesson 1, the title Surface Tension Specific. Welcome to the Lesson 1, the surface tension. In this lesson, we will explore the fascinating world of surface tension and its role in the behavior of fluids. Surface tension is responsible for some of the most interesting phenomena in nature, such as the formation of droplets, the ability of small insects to walk on water, and much more. By the end of this lesson, you will gain a deeper understanding of the forces and the play on the surface of liquids and how they impact both everyday experiences and scientific application. Let's get started and dive into the science behind surface tension. Specific learning outcomes. At the end of this lesson, the student should be able to first define the surface tension, second, describe the rule of intermolecular forces in affecting surface tension, third, distinguish between adhesive and cohesive forces, and fourth, solve problems on surface tension. So before we start or before we discuss the lesson, first we have having a motivational or prompting questions. Have you ever wondered how insects can move on the surface of water? Yes, those are fascinating questions. The ability to insect to work on water, like water striders, can be explained by surface tension. The surface tension of water creates a sort of film that resists being broken. The water strider's legs don't break through the surface because they're covered in tiny hairs that spread in weight evenly, creating enough upward force to keep it afloat. Surface tension is the tendency of a liquid surface to behave like a stretched elastic skin, caused by cohesive forces between molecules of the same substance. In water, these forces allows water striders to walk on the surface without sinking. Surface tension can be defined as the force per unit length acting on the surface to pull it together, and is mathematically represented by the formula Y is equal to F over L, whereas F is force, L is length, and Y is the coefficient of surface tension. The formula for surface tension is Y is equal to F over L, whereas F is the force or in newtons, L is the length or in meters along the surface, Y is the surface tension coefficients or measured in newtons per meters. In simpler terms, surface tension is the force that acts at the surface of a liquid, pulling the surface molecules inward to minimize surface area. The guidelines for calculations. When you do calculations, the following are some guidelines for you to follow. First, objects with one surface and a contact with water surface, you will use the equation Y is equal to F over L. Next, objects with two surfaces in contact with water surface, you will use the equation Y is equal to F over 2L. Next, all calculation will be restricted to circular loops, circular plate, and needle or razor. If circular objects are used to calculations, length or L is the circumstance of two R objects with one surface, object with two surfaces, or razor, or all flat objects, or needle, or all cylindrical objects.
Pull the loop
The
out of the
circular
oil
plate,
and spin
circular
tension,
loops, or
acting
rings.
around the circumference of the loop. Since the loop is circular, it has two surfaces in the contact with the oil, inside and out. Therefore, the total length of the loop, which are the surface tension acts on, is twice the circumference of the loop. Step 1. Calculate the circumference. The circumference of a circle is given by the formula L is equal to 2 over pi r. L is equal to 2 times 3.14 times 0.025 is equal to 0.157 m. Step 2. Surface tension formula. The surface tension Y is calculated using the formula is equal to Y is equal to F over 2Y. Substitute the values into the formula. Y is equal to 0.04 n over 2 times 0.157 m is equal to 0.04 over 0.314 is equal to 0.127 n over n.
The effects of a surface tension. Surface tension has several effects such as following lightweight objects or insects to walk in water, forming bubbles and shaping droplets into spheres due to cohesive forces. One important effect of surface tension is capillary action, where liquids rises in a narrow tubes against gravity. So it means surface tension is a force that acts at the surface of a liquid, causing it to behave like a stretched elastic skin. It has several noticeable effects. Insects walking in water. Due to the surface tension, the surface of water can support lightweight objects or insects without them sinking. The surface behaves like a thin skin holding them up. The formation of bubbles. Surface tension pulls the water molecules together, causing bubbles to form and adopt a spherical shape. This happens because the liquid surface molecules are attracted to each other, minimizing the surface area and forming a sphere. The bubbles and the liquid. The surface tension causes liquids to form spherical droplets as it minimizes the surface area. In the bubble, the pressure inside is higher than the pressure outside, and thus pressure difference depends on the surface tension or Y, and the bubble's radius or R. The relationship is given by the equation. The specific learning outcomes. First, at the end of the define laminar flow and turbulent flow. Second, explain the concept of viscosity. Third, cite some practical values of knowing the viscosity of a substance. So, it means viscosity is the resistance of a fluid to flow with subjective to an applied force. High viscosity fluids resist flow, while low viscosity fluids flow easily. It is determined by how strongly a moving layer of a fluid drags adjacent layers along with it. Viscosity is measured using a viscometer, which measure the rate at which fluid flows through a standard size orifice. So it means viscosity refers to a fluid resistance to flow when force is applied. It is essential how or thick or sticky a fluid is Fluids with high viscosity like honey or molasses are thicker and recessed flowing, while fluids with low viscosity like water or alcohol flow easily. The viscosity of a fluid is determined by the internal friction between its layers. When one layer of the fluid moves, it drags the adjacent layers along, and the stronger this drags, the higher the viscosity. To measure viscosity, a device called a viscometer is used to measure how quickly a fluid flows through a small standardized opening. The slower the fluid flows, the higher its viscosity. So now let's move on to laminar flow and viscosity. Viscosity is the property of fluids that determines how easily they flow. Fluids like juice, which flow quickly, how low viscosity, while syrup, which flows slowly and streaks to surfaces, has high viscosity. Viscosity is defined based on laminar flow, where fluid flows smoothly in layers without mixing, in contrast to turbulent flow, which involves swirling and mixing of fluids layer. So it means viscosity refers to how resistant a fluid is to flow. It's like the thickness or stickiness of a fluid. Liquids like juice, which flow easily and quickly, have low viscosity because their internal friction is minimal. On the other hand, liquids like syrup have high viscosity because they are thicker and recessed flowing, often sticking to surfaces. For the figure 2 illustrates how viscosity is measured using two parallel plates with a fluid between them. The bottom plate is fixed and the top plate is moved. Dragging the fluid along, the layers of fluid near the plates move at different speeds, with the top layer moving at velocity and the bottom layer at rest. The flow is laminar, meaning the layers do not mix. The force required to move the top plate at a constant speed depends on four factors: the speed, the area of the plate, the distance between the plates, and the fluid's viscosity. The force is directly proportional to, and the inversely proportional to, the equation defines viscosity and solving for gives. Viscosity is measured in terms of how a fluid recessed flow with is a unit being PARS Pascal seconds, equivalent to nm, or viscosities varies greatly between different fluids, with gases generally having much lower viscosities than liquids. Viscosity is also temperature dependent. For example, the viscosity of blood can be reduced by the aspirin, helping it flows from easily and reducing the risk of blood clots, which can contribute to preventing heart attacks when used over the long term in low doses. So it means viscosity can be measured using a viscometer, which determines the force needed to move through a liquid, or by simpler methods like observing how far a liquid moves on a slight incline over time. The basic concept is to assess how resistant a fluid is to flow. A fluid that flows quickly has low resistance, while one that requires more force to move has higher resistance. A fluid's resistance to flow increases with more internal friction. Why viscosity is important in daily life? Viscosity is important in many fields, not just in everyday life. For example, in lubrication for vehicles, the viscosity of oil affects friction, heat, and oil consumption, influencing how easily a car starts in hot or cold weather. In cooking, viscosity impacts how oils, fats, and soy sauce behave, affecting texture and consistency in dishes. In manufacturing, proper lubrication is essential for equipment efficiency and viscosity, affecting the protection of moving parts and preventing blockage. In medicine, the viscosity of fluids like blood is critical to viscosity can cause clots, while too low can lead to excessive bleeding, both of which can be life-threatening. Viscosity is important in various fields because it directly affects how fluids behave and interact with their environment. In vehicle lubrication, the viscosity of oil determines how effective it reduces friction, manages heat, and influences oil consumption, affecting how the car starts in both hot and cold weather. In cooking also, viscosity impacts the texture and consistency of oils, fats, and sauces, playing a crucial role in the preparation of dishes such as soup and stews. So now let's tackle in the module 4, which is the title of Fluid Dynamics. Fluid dynamics is complex as fluids can move in various ways, and we don't fully understand all their behaviors. For this lesson, we'll make a few assumptions. The fluid is uncompressible, or its density doesn't change. The flows of laminar, steady and constant, like water in a straight creek, and the fluid is non-viscous, no resistance to flow, unlike honey. With this assumption, we'll explore the characteristics of fluid's flow, the equation of continuity, and Bernoulli's equation. Fluid dynamics is the study of how fluids, liquids, and gases moves, but it's a complex subject because fluids can behave in many different ways, and we don't fully understand all of their properties and behaviors. To simplify things for this lesson, we make three case assumption about the fluid. Incompressible. This means the fluid's density doesn't change, so its volume stays the same no matter the pressure applied to it. For example, water is often treated as incompressible because its density doesn't significantly change under normal conditions. While laminar flow, the fluid flows smooth, steady layers without turbulence. This type of flow is predictable and constant, like water moving in a straight creek, where there are no sudden changes or chaotic swirling. Number 3, non-viscous. There is no resistance to the fluid's flow. Viscosity is the internal friction within a fluid that resists motion, like honey resisting flow more than water. But for this lesson, we assume the fluids has no such resistance. So now, let's move on to the lesson 1 with the title of Equation of Continuity. Of the study of the equanimity, this fundamental principle helps us understand how fluids behaves as it flows through a pipe or channel. Whether you're exploring this steady, predictable nature of incompressible fluids or working through practical application, the equation of continuity will guide you in understanding how flow rate is conserved along a fluid's path. Get ready to dive into the essential concept that explains how changes in a pipe area can affect that fluid velocity. It's a key to unlocking the mysteries of fluid dynamics. Specific learning outcomes. At the end of this lesson, the student should be able to first describe the characteristics of flow, second, explain the equation of continuity, third, describe the relationship between flow rate and velocity, third, motivation. Lesson 1, Equation of Continuity. Fluid dynamics studies how fluids behave in motion, which can be either steady or turbulent. In steady flow, the fluid's velocity remains constant at a given point, and its motion can be represented by streamlines, where closer streamlines indicates higher velocity. Fluids can be compressible like gases, which change volume with pressure, or incompressible, like liquids which don't change volume much under pressure. Fluids can also be viscous, flow slowly, or non-viscous, or flow easily. Underflow can be rotational swirling or irrotational or straight line motion. The chapter will focus on irrotational, incompressible, steady, and streamlined non-viscous flow. So it means fluid dynamics is the study of how fluids or liquid and gases moves. There are two main types of fluid flow, steady and turbulent. In steady flow, the fluid velocity remains constant at each point, and this flow can be visualized using streamlines, which shows the direction of the fluid's movement. When the streamlines are closer together, it means the fluid is moving. Fluids can also be categorized as compressible or incompressible. Gases are compressible, meaning their volume changes when pressure changes. Liquids, on the other hand, are generally incompressible, meaning their volume doesn't change much with pressure. Fluids can also be viscous or non-viscous. A viscous fluid flows slowly because it has internal friction, like honey, while a non-viscous fluid flows easily with a little resistance, like water. Additionally, fluid flows can be rational or irrotational. Rational flow involves swirling motion, whereas irrotational flow involves straight line movement without any spinning. For the chapter, the focus is on a very specific type of flow: irrotational, incompressible, steady, streamlined, non-viscous flow, which simplifies the study of fluid dynamics and helps in understanding the basic principle. So now let's move on the volume flow rate or Q. The volume flow rate or Q of a liquid is the amount of a fluid passing through a given cross-sectional area per unit time. It is defined the volume or the symbol of V divided by the time, the symbol of T, expressed as Q equals to V over T. In SI unit, this is measured in cubic meters per second or m cubed per second. The volume of a fluid portion in a pipe can be written as V is equal to ED, where A is the cross-sectional area and the D is the width of the fluid. Substituting into the flow rate formula, we get Q is equal to A times D over T. Since D times T is the speed or V of the fluid, the formula simplifies to Q is equal to AV, where A is the cross-sectional area and the V is the fluid speed. This formula is useful because the area A is easy to determine, especially in cylindrical pipes. In this example, we are using the equation of continuity to determine the speed of a fluid at a narrower point in the pipe. The flow rate, which is the product of the cross-sectional area of the pipe and the speed of the fluid, or Q is equal to AV, must remain constant throughout the pipe. Specific learning outcomes. First, explain the terms in Bernoulli's equation. Second, explain how Bernoulli's equation is related to conservation of energy. Third, explain how to derive Bernoulli's principle from Bernoulli's equation. Bernoulli's equation describes the relationship between pressure, velocity, and height in a fluid. It states that for an incompressible, frictionless fluid, the sum of pressure kinetic energy is equal to 1/2 PV squared, and potential energy, PGH, remains constant along a flow path. This equation is a form of the conservation of energy. In static fluids, when velocity is zero, pressure increases with depth. A constant depth, Bernoulli's principle shows that as the speed of a fluid increases, its pressure decreases. This principle explains fluid behaviors in situations like nozzles and Venturi methods, where flow speed increases and pressure drops in a narrow section of a pipe. So it means Bernoulli's equation explains how pressure, velocity, and height interact in a moving fluid. It states that the total energy in the fluid, which includes pressure energy, kinetic energy from the fluid's velocity, and the potential energy from its heights, remains constant as the fluid flows, assuming it's incompressible and frictionless. In conclusion, the study of fluid dynamics, including the equation of continuity, Bernoulli's principle, surface tension, and viscosity, reveals the fascinating ways fluids behave in various conditions. Understanding the equation of continuity helps us grasp how fluids flow and conserve, while Bernoulli's principle connects speed and pressure in a fluid system.